Our best theory of the universe, the standard model of cosmology, known as lambda CDM, lambda cold dark matter, might be fundamentally wrong. We are currently living through a pivotal moment in human history, an era where our understanding of the cosmos is shifting faster than it has in centuries. If we are fortunate, we are standing on the precipice of a revolution comparable to the shift from geocentrism to heliocentrism, or the realization that our Milky Way is but one of trillions of galaxies. The standard model under siege. For decades, the lambda CDM model provided a beautiful, cohesive narrative. It explained the Big Bang, the composition of matter, and the expansion of space. It matched our observations with such precision that many felt we had nearly deciphered the cosmic code. However, as our technology improved, culminating in the launch of the James Webb Space Telescope, JWST, cracks began to appear. These are not mere statistical flukes, they are fundamental mismatches that refuse to disappear with more data. Historically, when observations don't match theory, we face two paths: the Uranus path or the Mercury path. 2 centuries ago, Uranus's orbit was slightly off. Instead of discarding gravity, astronomers predicted a dark planet was pulling it, leading to the discovery of Neptune. But when Mercury's orbit failed to align with Newtonian physics, the answer wasn't more stuff, it was a new idea. Newtonian gravity had to be replaced by Einstein's general relativity. Today we must ask, are we looking for a cosmic Neptune, or do we need a cosmic Einstein? Crack 1. The defiance of the cosmological principle. One of the most sacred pillars of astronomy is the cosmological principle. It assumes that on a large enough scale, roughly 1 billion light-years, the universe is homogeneous and isotropic, meaning it looks the same everywhere and in every direction. This assumption allows us to believe that our local view is a fair sample of the whole. However, we have discovered cosmic monsters that shouldn't exist. The giant arc, a crescent of galaxies spanning 3.3 billion light-years. The Big Ring, a structure 1.3 billion light-years in diameter, found in the same neighborhood as the arc. The Hercules Corona Borealis Great Wall, an unfathomable filament stretching 10 billion light-years, nearly 10% of the observable universe. Statistically, these structures are so large, they defy the theoretical scale of homogeneity. If the universe is not uniform, we are like ants on a single cherry, trying to guess the flavor of a massive, diverse cake. Our entire standard model might just be a description of a local quirk rather than the universal truth. Crack 2. The Hubble Tension. A universe at 2 speeds. The Hubble Tension is perhaps the most famous crisis in modern physics. We measure the expansion rate of the universe, the Hubble constant h0, using 2 primary methods. 1. The early universe method, using the cosmic microwave background, the afterglow of the Big Bang. Planck's satellite data predicts an expansion rate of roughly 67 kilometers per second, MPC2. The late universe method, using standard candles like Cepheid variables and supernovae in nearby galaxies, we measure a rate of roughly 73 kilometers per second /MPC. The discrepancy is about 9%. In the past, error bars were large enough to bridge this gap. Today, the measurements are so precise that the chance of this being a fluke is less than 1 in a million. The universe is giving us 2 different answers to the same question. This suggests that our understanding of dark energy, or the way space-time stretches, is missing a vital component. Crack 3. The impossible early galaxies. The James Webb Space Telescope, JWST, was designed to see the first light, but it found something impossible. According to the standard model, large, mature galaxies should take billions of years to form through a slow process of hierarchical merging. Yet, JWST discovered massive galaxies, like ZFUDS 7329, that existed only 280 to 500 million years after the Big Bang. These are not small, chaotic clumps. They are grown-up galaxies with metal-rich stars. Because heavy elements like carbon and nitrogen are only forged in the hearts of stars that then explode, finding these elements in the infant universe implies that entire generations of stars lived and died before these galaxies even formed. It's like finding a PhD student in a kindergarten. The philosophical beauty of crisis. Why is this crisis exciting? Because in the philosophy of science, as described by Thomas Kuhn in The Structure of Scientific Revolutions, a crisis is the precursor to a paradigm shift. When a theory becomes cluttered with epicycles, complex fixes to keep a failing idea alive, it is a sign that a deeper truth is waiting to be discovered. The universe is misbehaving because it is telling us that our story is incomplete. We are currently grappling with other anomalies. The lithium problem. We see 300% less lithium-7 in the universe than the Big Bang Theory predicts. The cusp core problem, dark matter distributions in galaxy centers, don't match simulations. Evolving dark energy. Recent data from the DESI, Dark Energy Spectroscopic Instrument, suggests that dark energy might not be a constant, but something that changes over eons. Conclusion. Science does not move in a straight line. It moves in cycles of calm and chaos. The cosmological crisis is not a failure of astronomy. It is a sign of its vitality. We are witnessing the death of an old certainty and the birth of a new mystery. Whether the answer lies in early dark energy, modified Newtonian dynamics, MOND, or a radical rethink of space-time itself, the cosmos is proving to be far more unruly, chaotic, and magnificent than our equations ever dared to suggest. The universe is screaming that there is more to learn, and for those with the curiosity to listen, there has never been a better time to look up.